Hello. As you know, Chapter 4 of the textbook deals with acids and bases in organic chemistry, so we will do a few videos here specifically on acids and bases, kind of reviewing the material from general chemistry, and also kind of relating how acids and bases specifically deal with organic chemistry. Let's define what is an acid first. We're going to use the Bronsted-Lowry definition. This is far and away what most chemists use when they talk about acids and bases. So an acid, in the Bronsted-Lowry definition, an acid is any substance that may give away an H+. Now, H+ doesn't exist by itself, but it can be transferred from one place to another, just like if I hand you a dollar. The dollar doesn't ever have pre-existence. It's either in my hand or it's in your hand, but we talk about H+ as a thing that gets transferred from one place to another. So an acid has to have at least one hydrogen, and some examples given here. Obviously, hydrochloric acid, or I should say hydrogen chloride, is an acid, but water is also an acid because it can give away one of its hydrogens. This molecule is acetic acid, and it's a carboxylic acid. It can give away that hydrogen right there. I'll give you a little side light here. Under extreme conditions, those hydrogens can also be given away, but typically hydrogens on carbon are not acidic, so it's the hydrogen on oxygen that gets given away in an acetic acid molecule. This is the ammonium ion, NH4+. It's an acid, so acids can be neutral. They can also be positive, and in some cases they can even be negative, as we'll see in a minute. But as long as it can give away an H+, it's an acid. So ammonium can give away an H+, it's an acid. H3O+, the hydronium ion, it's kind of the definition of acids, at least in aqueous solution. It can give away an H+. This is bicarbonate. I mentioned a minute ago acids can be negative. Well, if this gives away an H+, of course, then that becomes negative too, because it's giving away a positive. In any case, bicarbonate can be an acid, and there are many, many, many others as well. So what's the definition of a base? Well, a base is any substance that can pick up an H+ from an acid. So obviously you have to have both an acid and a base in order to transfer an H+, at least in the Bronsted-Lowry model. So what do you have to have in order to be a base? Well, you have to have at least one pair of electrons that you can use to attach to that H+ that's going to be picked up. So water can be a base. Well, we saw water up here as possibly an acid. Here we see water again as possibly a base, and it is. It can be either one. So if something is going to give away an H+, the water can pick it up, or if something wants to pick up an H+, water can give away. So it can be both an acid and a base. But it has lone pairs on the oxygen, and it's those lone pairs that can pick up, or one of those lone pairs that can pick up an H+. Hydroxide has 3 lone pairs. It's obviously a sort of a standard base. It can pick up an H+ easily, become water. Cyanide is a base. It can pick up an H+. Carbonate is a base. It can pick up H+. Obviously, it has a negative too. When it picks up an H+, it will become bicarbonate, and so that's the conjugate acid of that base. We'll see a lot more about conjugate acids and bases here in a few minutes. Ammonia has a lone pair on the nitrogen. It can pick up an H+. And here's kind of an unusual one. This is called an acetylide ion. It has a lone pair on carbon and a negative charge, and it can pick up an H+. So, as we said, an acid is any substance that may give away an H+. So, for example, HCl easily gives away an H+, and it becomes Cl- when it does so. That's called the conjugate base of the acid. Water can give away an H+, not so easily, because it's a much weaker acid, but it can give away an H+, and when it does so, it becomes OH-, and so that's the conjugate base of that acid. And conversely, a base is any substance that can pick up an H+. So examples, hydroxide can easily pick up an H+, and when it does so, it becomes water. And ammonia can also pick up an H+. Again, not so easily in this case because ammonia is a much weaker base than hydroxide is, but ammonia can pick up an H+, and in so doing it becomes NH4+, or ammonium ion. So again, that's the conjugate acid of that base. As I said, when an acid gives away its H+, it becomes the conjugate base of that acid. So HCl becomes Cl-, that's the conjugate base of that acid. Sulfuric acid gives away an H+, and it becomes HSO4-, or bisulfate. That's the conjugate base of that acid. Bisulfate itself is an acid, and it can give away an H+ to become SO4- too. So that's the conjugate base of that acid. That's the conjugate base of that acid. So that's the base, the conjugate base of that acid. That's the conjugate acid of that base. So again, like water, it serves two roles. It can be a base, it can be an acid. Same thing with water. H3O plus, when it gives away an H plus, becomes H2O, which is then the conjugate base, but H2O can turn around and be an acid and give away an H plus and become hydroxide, so that's the conjugate base of that acid. And as we saw, ammonium ion gives away an H plus and it becomes NH3. When a base picks up an H plus, it becomes a conjugate acid. So Cl minus becomes HCl, that's the conjugate acid of that base. As we saw a minute ago, that's the conjugate base of that acid. So they constitute a pair, a conjugate acid and a conjugate base of each other. Similarly, HSO4 minus is a base and it becomes H2SO4 when it picks up an H plus, so that's the conjugate acid, that's the conjugate base in that pair. Water becomes H3O plus when it picks up an H plus, so that's the conjugate acid of that base. Hydroxide becomes water when it picks up an H plus, so that's the conjugate acid of that base. So again, a pair. Hydroxide is the base, water is the acid. Water is the base, H3O plus is the acid. And Cn minus, when it picks up an H plus, becomes HCN. That's the conjugate acid, that's the conjugate base in that particular pair. So take a minute and we'll pause the video and see if you can fill in the blanks in this table. Obviously HBr is the conjugate acid, Br minus is the conjugate base, but I want you to fill in what's the conjugate acid of this base, what's the conjugate base of this acid, what's the conjugate acid of this base, what's the conjugate base of this acid, what's the conjugate base of this acid. Be careful with this one because that's normally thought of as a base, but I'm putting it in the acid column, so it must have a conjugate base in this column. Again, water, what's its conjugate acid, and water, what's its conjugate base. So stop the video and fill those in, and we'll see what the answer is here in a minute. So for an acid to give away an H plus, there must be a base to give it to. For a base to pick up an H plus, there must be an acid to give it to, as we've seen before. And basically what I'm saying here is that you can take any acid, ones from the list that we saw before, or any other acid, and there are literally thousands of different acids. You can put any acid you want to in the presence of any base you want to, and there are literally thousands of bases. So pick an acid, pick a base, and then you can predict what the products would be. The way you do that is you start by predicting which one of these two substances is the acid and which one is the base. We talked about this quite a bit in general chemistry. I've picked two examples here that are organic compounds. So which one is the acid and which one is the base? One trap you don't want to fall into is this. You see OH here, you think, oh, that's hydroxide. I know that hydroxide is a base, so therefore this must be the base. But notice that that's not hydroxide. This is a covalent bond between the oxygen and the carbon. So this is not OH minus. This is actually just an alcohol in which the oxygen is covalently part of the molecule. It's not hydroxide. So it could be an acid or it could be a base. It depends on what the other thing is. So let's look at one or the other of these and see if we can get any handle on which one's the acid and which one's the base. Well, here's a hint. Since this has a positive charge and hydrogen's on nitrogen, it's probably the acid. And that would be a good guess in this case. It's harder to tell by looking at this because this could be an acid or it could be a base, but this clearly is the acid in this case. And therefore the other one must be the base. If one's the acid and this is going to be an acid-base reaction, then the other one must be the base. Then we have to decide what's going to happen. So here's the acid, here's the base. What do acids do? They give away an H plus to become their conjugate base. So if this gives away an H plus, it gives away not only one of the three hydrogens, it also gives away the positive charge, so it becomes CH3NH2 without a positive charge. And if this is the base, then it must pick up an H plus, so it becomes, instead of just CH3CH2OH, it becomes CH3CH2OH2, picking up an extra hydrogen. And it also picks up the positive charge, so it becomes overall positive. Now, you can do the same thing for any acid and any base. I want you to decide which one is the acid and which one is the base, and then go ahead and take the H plus off the acid and put it onto the base. See if you can come up with the answer. Now, there are many organic compounds that are acids and many that are bases. Those that are commonly found and those that don't have charges, in other words, neutral compounds that are acids and or bases. There's basically four kinds. There are these things called sulfonic acids. Sulfonic acids have a carbon group, so that's what the R stands for, and then a sulfur with three oxygens attached, and then a hydrogen attached to one of those three oxygens. These turn out to be very strong acids, kind of like sulfuric acid. In fact, these are very similar to sulfuric acid, both in structure and in acidity. The other kind is carboxylic acid, and we've seen them before. Just a carbon group attached to a CO2 with an H, and hydrogen's attached to one of the two oxygens of the carboxylic acid. And those turn out to be not real strong acids, but strong enough that the word acid actually appears in their name. And then there are things called phenols, and phenols are benzene rings. That's what the AR stands for, is a benzene ring. The benzene ring may have other things attached to it or may not have other things attached to it, but it has at least one OH attached to it, and that OH is what makes it an acid. So these are called phenols. You might say, well, isn't that the same thing as an alcohol? And you may remember that phenols really is a separate category. They're not alcohols, and this is the main reason why they're not alcohols, is because they are much stronger acids than regular alcohols are. So phenols are acids. Now, I said a minute ago they're much stronger than alcohols, but that doesn't mean they're strong acids. In fact, phenols are pretty weak acids. It's just that they're stronger than alcohols are. And then there's really only one kind of organic base, and those are the amines. Remember when we talked about functional groups, the amines come in three types. There's a nitrogen with one carbon group and two hydrogens, those are called primary amines. A nitrogen with two carbon groups and one hydrogen, those are called secondary amines. And a nitrogen with three carbon groups, so that's a tertiary amine. But they're really all considered in one category. Each nitrogen has a lone pair on it, and so any one of those nitrogens can pick up an H plus relatively easily. And that's the definition of what a base is, something that can pick up an H plus. And so therefore amines are bases. Now, as shown here, there are other very weak acids that are organic compounds, primarily alcohols. So the ROH, as I mentioned ago, if that's just a carbon group, it's not a benzene ring, and this is also not a carboxylic acid, obviously, but just a regular alcohol. Those are also acids because they can give away an H plus. It's just that they're very, very weak acids, so they don't give away the H plus. Normally, in other words, if we use hydroxide as the base, it's not really strong enough to pull off that H plus, and therefore these are considered to be very weak acids and normally not considered in the quote acid families at all, but they can act as acids. And the other one is alkynes. Interestingly enough, if you have the hydrogen on the end of a triple bond, that hydrogen can be pulled off. In other words, it can give away its H plus, but it has to be a very, very strong base to do that. So alkynes are not normally thought of as acids, but they can be if the base is strong enough. When I say strong enough, I mean it has to be stronger than hydroxide. So NH2 minus is a base, and it's sometimes used to pull off the H plus from the end of an alkyne. And H minus itself is a simple base called hydride, but a strong base, and it can pull off the H plus from alcohols and also from alkynes. And then there are other acids that are charged acids, so we don't think of them as organic acids, but they really are because they just happen to have a charge on them, and those are in fact the conjugate acids of the amines we saw a minute ago. So if you put an H plus onto the base that's a primary amine, you get a primary ammonium ion, and if it's a secondary amine and you put an extra H plus onto it, you get a secondary ammonium ion. And if you put an H plus onto a tertiary amine, you get a tertiary ammonium ion. So the amines are the bases, and then these three are the conjugate acids, so they fit into the category of acids. And there are also charged bases that are the conjugate bases of a neutral acid. So RO minus is the conjugate base of an alcohol, and so technically it's an organic base. Those are called alkoxides, by the way. This would be the conjugate base of a carboxylic acid, and it's an organic compound, so it's an organic base. And this would be the conjugate base of an alkyne with a hydrogen on the end. If you take off that hydrogen, you get a negative charge on that carbon. So this is the conjugate base of that acid. So again, these are organic bases. Okay, so in summary, I've listed out here the main kinds of acids and the conjugate bases that we would see. So those kinds of organic acids that are strong enough to react with hydroxide, as I said, sulfonic acids, those are very strong acids. Carboxylic acids are weak ones, but they're still strong enough to react with hydroxide. Phenols, very weak acids, but strong enough to react with hydroxide. And ammonium ions, again, weak acids, but strong enough to react with hydroxide. And the conjugate bases of these would be the sulfonates, the carboxylates, the phenoxides, conjugate base of phenols, and the amines, which are conjugate bases of ammonium ions. Of all of these conjugate bases, these are the only ones that are neutral. So remember a minute ago we said there's only one kind of neutral organic base, and that's amines. Well, here we see it as a conjugate base of that acid. And then there are a couple of kinds of organic compounds that are weak acids that are weak enough that they don't even react with hydroxide. You need an especially strong base to do that, and those are the alcohols, and their conjugate bases are alkoxides, and alkynes, and their conjugate bases are acetylides.